Okay, and so as I mentioned in the abstract, so the proof of the so-called Agmon estimates or Agmon leap estimate at the beginning was given in order to control the decay of eigenfunction of n-body problem. And so this was more control of the decay of the eigenfunctions at infinity than the control that we meet in the, for example, in this landscape, in the landscape picture. So I changed a little the data to say. So essentially, the first paper where this technique appears is in 1979. Usually, one refers to a paper of 1982, but the idea was already going through the specialists, starting from the end of the 70s. And to Agmon is still alive, so 1970. 97 years old. And so here are the title of what I can speak about. Probably I will, depending on the time going on, I will not describe all the stuff. So the first item corresponds to what was done before. Then the second item corresponds to the way one can adapt the Agmon strategy to work in the context of semi-classical analysis. And then I will try to give some relatively detailed presentation of how one treats the simplest model, the so-called double-well symmetric problem, where at the same time Agmon estimates appear, and also this gives application to the so-called turning effect. And then there are various possible subjects. The analysis of the so-called resonant wells, so the analysis of the magnetic Schrödinger operator, where in different contexts, the way you can also do Agmon estimates in another context, where the so-called type binding model. Then we can look at how Agmon estimates are used for other operators, like the Schrödinger operator. And so this includes Klein-Gordon, Dirac, Katz model, Harper model. Then another item could be to analyze what's going on with the so-called magnetic bottles. So here we have no more any electric potential, but only a magnetic field, and we can see how localization occur. This time not due to the electric potential, but due to the magnetic field. So the confining effect is due to the magnetic field. And then other subjects which have been developed a lot, decay estimate in superconductivity. So for example, surface superconductivity can be interpreted as a localization, is very strongly related to the localization of eigenfunction of Schrödinger operator. But this time it's a boundary effect. I put the item decay estimate for the Robin problem, but I think Konstantin Pokrashkin will speak about that, and so I will not look at this. And finally, I wanted to come back to the landscape function, to discuss a little what I have understood, not so much. But, okay, so let's start. Let's start with this so-called Agmon estimate. And I found the best way was to look at the introduction of a paper which appeared in '82 by Carmona and Simon, presenting this. So this arrived in '82, and the idea was to describe the behavior of the ground state phi, and so these results are presented as some improvement of Agmon estimate. In Agmon estimate, you have mainly upper bound, and here the result which is presented here. So you have the ground state to take the logarithm, and you divide by some suitable function rho, which is explicit and contain many cases of potential that will be rather vague on the assumptions, and then this gives you the asymptotic behavior of the ground state at infinity.
So where is Agmon estimate in this? Where is? Could you just say a few words what Agmon estimates are? Because
let's wait a little bit. So for the moment, weighted estimate is exactly what I wrote for some given rho that I have not defined at the moment.
Figure out what rho is. It's inside what rho is.
This is the description of this rho which is the Agmon, so-called Agmon distance. And so this is the Agmon estimate in an optimal way, because you look at the limit, not only at the upper. So it's a ground state, so phi does not vanish. Okay, so here is a kind of history about the upper bound. There is a lot of literature in the 70s about that, and so this is Agmon in 1979, which gives essentially the general case, including the end-loop problem. But in the case of potential going to infinity at infinity, one should also refer to Leibniz. So this is why sometimes we call the Agmon distance the Leibniz-Agmon is upper bound. Okay, so now here is what usually you call. So, for example, in the case by Inter, we call an Agmon estimate. And the strategy of Agmon was to say that you can show an estimate of this type as soon as rho of x satisfies this kind of estimate. Rho of x squared less than v of x. So, historically, by another method, one should also refer to Jean-Michel Combe, and I don't remember the first name of Thomas, so the so-called Combe-Thomas method. Okay, so I will come back to this rho of x later. But then 2 years later, you have we start to look at the use of Agmon estimate in the semi-classical context. So it starts essentially in '83, at least at the level of the publication. So everybody, that is Barry Simon on one side and me and in collaboration with Jan, has just start to work on this a little earlier. But so the first announcement, published announcement, is by Barry Simon, which exhibits for the first time the role of the Agmon estimate in the semi-classical context. So now we are not analyzing the behavior of the eigenfunction at infinity, but we take some region in Rn, and we look, we normalize the L2 norm of the eigenfunction in L2 of Rn, and we look at the eigenfunction depends on the parameter h, the classical parameter, and we look at the L2 norm in a given region and try to analyze if this quantity tends to 0 and how it tends to 0. Okay, so I have tried to write things in order to satisfy everybody at the level of the priority. So, so beginning of 1983, there was this note by Barry Simon, and then two preprints, relatively independent preprints, were written in this paper, HS1 and Simon 2. And so at the end of 1983, we have an exchange of preprints. And so in the publication, the final publication is in 1984. So what one can say is that the techniques we develop are much more general than the techniques of Barry Simon, which were limited to the first, or the two first eigenvalues. But in the paper of Barry Simon, you have a probabilistic approach, which was already present in the paper of Carmona-Simon, which has an independent interest. And so, looking, for example, at present paper by Steiner-Berger about the landscape function, is coming back to this kind of definition. So there are other mathematicians or physicists who claim to have also the result about the bubble well problem at about the same time, including Maslov. As far as we have understood, the proof does not seem complete, or it's only true on the very strong assumption on the potential at infinity, because the basic role of Agmon estimate, which is present in the two papers here and here, here and here, is completely overlooked. So just this notion of localization of the eigenfunction is not apparently clear. Okay. So sorry. Okay. Let's see. Yes. Okay. So as I said, I will try to give a relatively detailed proof. Maybe I have not so much time, but just to see what is the basic technique. And this basic technique, after that, has been used in all the contexts I have described. And so what is remarkable is the simplicity of the technique. And essentially, you start from an identity. And here, at this moment, phi is completely general. And here, you have just one integration by part. So the question of the boundary here is solved by assuming that u is at the boundary 0. And you don't need so much regularity on the phase phi. It should be Lipschitz. So I put rather strong regularity, and here, this is just for convenience, but you can also work with much weaker assumption on V inside omega. Okay? So I have written this bounded operator, but sometimes you can have interest to write this omega equal Rn. So in this sense, you also recover question at infinity. So here also there is some small parameter h, but at this level, this identity is completely universal. So, and this is important because, for example, later, if you want to apply this kind of technique to the landscape function, you have no semi-classical parameter, and you just try to do universal estimate.
Sorry,
yes?
comment what tells us this identity? what do you learn with, from this identity?
I think you should wait.
Okay, but it's really confused because the artistic view of some equations.
I read you some
makes some substance.
I will show you in the next slide what is going on with this.
Maybe before it would be worse to say the meaning of the equation. So the bottom of the equation is just an exponential weight on the inner product with the operator. That's the bottom. And then the top splits it by integration by parts into two pieces. One of them is kinetic energy, with the gradient term.
And then
the other one is a balance, but it's a fight between the potential and the rate of change of the exponential weight. It's the gradient of phi. Okay, so and magically it's just telling you exactly how much, and then the plan is to optimize phi.
Okay, but I think it would be if you wait a little bit.
They won't see the identity.
I was planning to this, but for the moment this is just an identity.
But if it's sitting in front of you, you can see it. Whereas later you maybe not, unless you rewrite the identity.
Maybe if you look at this term, you can if I come back to what I wrote here, you see why it's interesting to try to find a phi which satisfies this, and to choose the best one. Actually, we need some epsilon to work correctly. Okay. Okay. So here is what I can do starting from this identity. So I have added the eigenvalue lambda h. So, and if I apply this identity, for example, for an eigenfunction, so one term disappears, this term disappears completely, and you get this. Now, if you forget this term, this positive term, you get this. And so you can also, assuming that lambda h is less than a, you get this. And so in some sense, you see that you control the L2 norm in a weighted space in the region where this quantity is positive. By you control this by in the region where it's negative, you put on the other side, and so you have an amount. So this is true for any phi, but now you appear to have Agmon distance. So you define the so-called classical region, v of x less than e, and you change the metric by multiplying by the potential v minus e plus. So this is a degenerate metric in the sense it's zero in the classical region, and it measures distance in the so-called forbidden region. And associated to this metric, you have a distance. And this distance can be defined also in this way. So that is the infimum over the path going from a point x to y with the weight which is here.
Sorry, one basic question about that distance. Does it come from a like a Riemannian metric or something? Does it come from a Riemannian metric? Is there some smoothness? Or the distance you wrote on the previous slide?
Oh, it's not completely smooth.
Oh, but
it's but so it's enough to. It's enough. Essentially,
it's a degenerate distance, and it has the same smoothness as v. So
essentially, the v, you should understand that v less than e, at least in the connected case, is just one part. Then it's a little degenerate at infinity. Yeah, you can have more information if you say more about v, but in general you don't. And so
Just could you maybe draw a picture of what's going on? What's the goal of the game? Was that suspect physicists and them actually don't know where.
Okay, I think we'll lose time. Wait a little. If you change the order of the presentation, I will never finish. So, starting from this, you can do what you are doing in a Riemann space. So you have a standard inequality for the distance, and you see that in particular, you have this property. And so here you start to understand why rho of x, which the research of the rho of x is quite closely related to this Agmon distance. And so the best rho of x is to take the distance to the well, to some. And so now so it's a little technical because you have to play between this region, this classical region, and the outside region. And so in your choice of phi of x, you should give some distance. But essentially, now we can precisely control the decay of the eigenfunctions. And so what you get is now that for this distance to v of x less than e, so this distance is d of x, you get this kind of estimate on any compact in the forbidden region. This is the decay state. So I take as phi of x or rho of x, depending on the slides, this quantity, where d of x is the Agmon distance. So, and the proof is just to play with essentially with what I wrote here. Okay, so you see that essentially, once you have the right notion, it's a free lines proof. And so, and this is why it's so useful and so flexible. And you have so here I have played with specific parameters, but you can you follow very strongly the proof. And so if you want to control with respect to parameter, it's not hopeless. If you have other parameters. Okay.
Just a question about what is the role of H in all these computations so far up to now?
The role of H is also is here, that I have assumed that lambda H is less than A. So of course, actually.
Maybe the question was more elementary, just the definition of the operator. It's h squared plus u.
I think you can take H equal to 1, and it's, you don't assume it to be small.
Oh yes, but at the end, yes, but it's for H small.
The point of the entire thing was that somehow when you have a, so in 1D, I'll draw a picture. In 1D, every physicist knows, and most mathematicians know, that when you have an energy in a well, which is below the energy everywhere else, you have an exponential decay, so the rest of V, which is above this energy level. In 1D, it's trivial. You can imagine that if you rotate this picture, you get the same in 2D and so on. But then the question is, if the potential is not rotational invariant, how do you figure out the exact rate of decay? I mean, imagine a very complicated potential which has nothing to do with rotational invariance. How do you know how fast it decays? So this entire game is about figuring out the exact rate of decay. And then towards the question of H, by means of making H smaller and smaller, you are deeper and deeper in the well, and so you have more of V to play with in some sense. So it's not, it's just a parameter in the proof that factually when you are applying it, if H is small, you are sitting at the bottom of the well, so you have a lot of exponential decay, you have a lot of
Okay.
Sorry.
So this here is a specific theorem with the assumptions and so for the decay. So now the first assumption is written in order to that as h tends to 0, we are sure that we have eigenvalues. We are below the essential spectrum because this is a lower bound for the essential spectrum. And then here is what you get. So I put here d, and so in this way I have a loss here of epsilon. So the information becomes interesting for d larger than epsilon. That is in a region where the distance is larger than epsilon. But the estimate is for any epsilon. Now you, under additional assumption v, you can take epsilon depending on h. And so you...
So what does that do now?
What?
D in that...
D is the Agmon distance to the classical region. Oh, sorry. D of x less than a.
Okay, thank you.
So the message is clear. It's the eigenfunction lives in the classical region as h tends to 0. And the second message is that outside of the classical region it decays, like the distance exponential minus the distance to the classical region. So the first application is that if you look to two Dirichlet problem in open set omega 1 and omega 2 containing a well that is, I assume now that the classical region is just connected, and I call well the region v of x less than e. Then if I change a little the problem, the variation of the spectrum below the energy E is exponentially small and can be measured very precise. Note that there is a small assumption. So when looking at some interval, I have a small assumption which corresponds to the idea that the ends of the interval should be in a gap of the spectrum. To compare two spectral problems, you should take an interval where you have some control of the gaps at the ends. Because if not, you could have some eigenvalue which is just leaving the end of it. In the semi-classical context, this condition is very weak because we know that there are always gaps which are not too small due to the counting of the eigenvalues. The Weitz formula says that you cannot have too many eigenvalues in the small interval. So I can always find an interval, a gap which is for the larger than some h to some power n, where there are no spectra. Okay, so this is the first application. The second application was this double well, symmetric double well problem. So in 1D it's well known. It appears in many. There was a huge literature, more or less rigorous. This is also an exercise in Landau sheets, but in dimension larger than 2, this problem was not solved at the time. So can consider that it was solved for the first time in the beginning of '83. Okay, so I think so. I was going much more slowly than expected, but okay. So I just recall what is the symmetric double well problem. So you have a potential, you have a symmetry, and so you have two wells which are exchanged by symmetry. And you want to understand first, at least, this was the case considered by Barry Simon, the two lowest eigenvalues. So first, if you decouple the two wells, you can look at the analysis related to one well. And so you have the so-called harmonic approximation, assuming that V has a non-degenerate minimum, which says which gives you a rather weak expansion in powers of H. And then, using the previous result, you know that this gives you the spectrum of the two first eigenvalues modulo some exponentially small term. That means that there exist two eigenvalues for the double well problem, which are exponentially close to the eigenvalue of one well problem. And then I have no time to. The second point is that you construct a basis of the spectral space attached to this two first space. You construct a specific basis consisting of two functions. There are no more eigenfunctions. Two functions which are strongly localized for the first one in the left well and for the second one in the right well. So this basis is obtained by starting from the construction of a one well eigenfunction and then projecting on this eigenspace. Now the role of the Agmon distance is to control very precisely the difference between the one well eigenfunction and this projection in a suitable way. Okay, I think I have to go. Yes. Maybe this is this point which is basic here. That by projecting the one well eigenfunction you have a very small error. That is, it's not simply small in L2 norm, but it's a weighted control, where you add to the distance to one of the well, d of u1, u2, the distance between the two wells. So once you have this, then you look at what is done usually formally in the physics literature, and then you arrive to a formula of this type. But then the last step is to show that in this special basis and in the region where you see this stock formula appearing, you can approximate the object by the WKB expansion. So it's wrong that an eigenfunction in dimension larger than 2 is overall approximated by the WKB solution. So this was the main point, which makes much easier the 1D case, where you directly use a WKB representation of the eigenfunction to the case where you are in dimension larger than 2.
What is WKB?
WKB is the research of a formal solution of this type. So you put this in the so here I take the case of a non-degenerate well, and so you put on the operator this expansion. So A of xh has also an expansion for words of H. And so the formula for the splitting was relatively easy to obtain if you formally replace in the expression in the formula the function by the WKB exponent. But the point is to control the comparison between the WKB solution and the eigenfunction. Okay. And so, okay, so at the end you get a very precise formula, which is here. So here there is an exponentially small term, which is the Agmon distance between the two wells for the energy corresponding to infimum of V. And then you get some integral that you can treat by the, under some additional assumption, you can treat by the Laplace integral method. And then you get a complete expansion for this. So this is what we get in the paper with Sjöström. So in the paper of Barry Simon, I think he's only obtaining the main term, not the complete expansion. Okay. So just a remark, inspired by sometimes what you are doing with the landscape function. This is very difficult to look at highly excited states. So you can imagine, there is again a double well problem for excited state. But at least when you arrive to the next critical point, the situation is much difficult to control. So it's by this approach you can control a finite number of eigenvalues, finite meaning independent of h. But if you want to go higher and see the interaction and the tunneling for excited states, it's much more difficult. So I give a few references here.
You just mean another minimum?
No. For the moment, I was just meaning it's already difficult in 1D. You try to look at what's going on at an energy which is higher. I no more analyze the two first eigenvalues.
Right. So what I'm asking is, even in the 1D picture, you're talking about 3 wells. That's okay, right?
Okay.
As opposed to getting a problem.
For 3 wells, there is a difficulty to define in 1D to define a symmetric 3 wells problem. Symmetric 3 wells. Yes, because
so
if it's not symmetric, it's more dangerous. And so you can analyze this kind of situation case by case. And one situation of this type is what I call non-resident well. So I can explain 2 cases. So if okay, depends on then it depends on the size of the curvature. So here I've written, as symmetric, I've written the curvature here. So the ground state will live here. And then for the second eigenvalue and the third one, assuming that the second level here is higher than this one. So what is the turning between these two? So in the previous approach, the distance which appeared was the distance between the wells. But here, you can show, so this is a second paper of Sjöström, you can show that the distance which is relevant for this double well problem, for the second one and third one, is the Agmon distance between these 2 parts. That is that you go through the non-resonant well and you can put.
Yeah, this is very important for the Agmon.
So, but this is very difficult to prove this kind of thing.
So you mean that
because you
more generally, if you are between 2 wells,
if you have other wells between the two wells, which are not resonant in some sense, then the tunneling go on. So this is this needs a very fine analysis, but I think it's important to mention.
This is important. Well, it's very important because you have to pass through one to get to the other.
So there is another case.
So can I ask you one question with respect to this? Was there any systematic study of, I don't know, inductive or something like this? When there are many wells? Is there any systematic study, inductive or something like this, when there are many wells?
Oh, yes,
I'm aware of papers.
Yes, so there are many papers.
Well, but specifically for this question, so I'm aware of papers in your work with the two wells. And I mean, intuitively, hand-wavingly, it's clear, you know, what to do if there is disturbed, but I would really want to see, you know, if there is some sort of uniform statement towards it, so that...
I think it's difficult to have a uniform statement because there are so many cases that I will give another paper where we have an infinite number of wells, but I cannot give you any universal statement. So another interesting case was, you start from the symmetric case, and this was an effect mentioned by Barry Simon, called the free of the left. So you just modify a little here, a little higher. So what's going on? About localization. Then immediately, if it's here, the ground state lives on the left and the right, and the second eigenfunction lives on the right. Yeah, this is very, very unstable. So you just change a little, so here. So if you change here, this will not be the case.
So what happens? Could you repeat that?
I repeat. So for the double well problem, the ground state is living symmetrically in the two wells, and the second eigenfunction is living antisymmetrically in the wells. Now, if you perturb just a little here, far from the bottom, but between the two wells,
it's where the doubling occurs. It's where the doubling occurs. Then
immediately the ground state will live on the lowest part, on the left, and the second one will be to the right. And this is very natural, but this is a consequence of a rather fine analysis of the. So when I described the double well problem, I said, in some sense, that I can compute an interaction matrix, a 2x2 matrix, corresponding to the projection for the two first eigenvalues. And then I can compute very precisely the different terms in this 2x2 matrix. So in the symmetric case, essentially, if I forget the diagonal, where the two are the same, I have a matrix which is simply some turning effect, 0, 1, 1, 0. And so the answer is that the first eigenfunction is, in this basis, is 1, 1, and the second one is 1 minus 1. Now if I start to perturb here, this is the free of the Lefebvre effect. Then immediately, if you look at the eigenvectors.
What if you look at the space span by the first two eigenvectors?
What is?
You look at the eigenspace, the span of the first two eigenfunctions.
So as I described, the eigenspace of the double vector problem corresponding to the two first eigenvalues is closed to a space that I construct by looking at the left problem and the right problem.
So that doesn't.
That's the symmetric state.
So that gets
very
stability.
stable. The two-dimensional space.
No, the two-dimensional space is stable, but the localization inside this is very unstable. Okay.
Can I ask you what's the Witten Laplacian?
Okay, I think I have more or less at the first tenth of my talk. So, I think. I think so. I will give the slides, and then I can of course answer to. I just try to mention all the cases where localization play an important role. Okay, so the magnetic case, so I will be very fast. At the beginning, we keep V, and we just add some magnetic. And so essentially, we keep the energy identity, except that we have to put some real part. And so the first message is that the eigenfunction decay at least as in the case A equals 0. But the second message is that it's not optimal. It could be not optimal. And so when it is optimal under very strong assumption, either that A is small enough, so that you are sufficiently close to the case without magnetic potential, or you can go a little further by using analyticity assumption. Second point, I don't remember which point it is, infinite number of wells. So it's natural to, for example, to look at the case of a periodic potential, or more generally in the context of random potential, you have many wells, and essentially the basic idea of this reduction by constructing localized first a basis of localized functions describing all the eigenspace works with modulo some control, and so you can play in different way for this situation. So maybe the most general paper is by Carlson, a student, a former student of Johannes Jostrand. And in a special case where we have our paper on Harper's models use also this. We're discussing with Frederick Klopp, because I did not remember very well, but Frederick Klopp in his PhD thesis, in papers following just the PhD thesis, was using this in the context of random electric potential. Okay, so I think I go on. For the tight binding, I just wanted to mention one point. I mentioned this because effectively, for the landscape function, you meet a situation which is not semi-classical. So you can essentially follow the same strategy as in the semi-classical context in the so-called tight binding model in this sense. So typically you have a potential small v, which is, say, with compact support to simplify, and you translate in one direction, minus r. And so the potential is the sum of two potentials which are found, whose distance is increasing with r. And then, so here you have no need to use the WKB approximation. It's best to use as one well model the problem minus Laplacian plus small v. So you take the eigenfunction of this and then you translate suitably, you project. You can follow all the strategy which was given. You can show Agmon estimate in this case. This time this Agmon estimate are related to the behavior of the eigenfunction of minus delta plus v at infinity, and then you go on and can determine for example, treat the double well problem in the limit r tends to infinity. So there are quite recent contributions by around Charlie Pfefferman and Michael Weinstein, where this kind of question reappear. Okay. Localization for other operators. So of course we have tried to see if the localization can be analyzed for other operators. And so if you analyze more generally what you are doing when looking at Agmon estimate, you are trying to consider the initial operator and look at exponential -5/h ph exponential 5/h. So at the level of the symbol of the operator, this corresponds to a translation of the symbol in the complex. And so this was at the beginning rather surprising. When we start to look at the double well problem, we were rather naive, and we think that we have to assume at the same time analyticity in X and Xi. But as you have seen, Agmon estimates show that you don't need any analyticity to measure this exponentially small effect. And so, but what is surely yes?
I'm a big reservoir of a stupid question, but what does it mean, the symbol of
Okay. So in the case it's a differential operator, you replace 1/i d over dj by psi j. So this is a okay. Then you get a function of x and xi. So maybe for the physicists you would prefer pj, or this is q and p. Okay, so you prefer this q and p. So this is the symbol. And the operator I am considering is the quantization of the symbol which is defined on this t star of the. Okay, but so if you want to understand Agmon estimate in a larger context, you have to look to this. And actually, if you take the Agmon case, the real part, because you look at real part of PUU, is psi square minus psi prime x square plus v of x. So in some sense, the validity of Agmon estimate is related to some ellipticity property of the real part of the symbol. There is a brother estimate called Kalman estimate, which is a little different. But, and so an interesting case is Klein-Gordon. Why? Because the symbol is square root of 1 plus psi square plus v of x. And when you go in the complex, at sometimes you meet some singularity. That, in some cases, you can see on the tunneling effect this problem that you meet this psi square equal -1. So I'm very short on this. Just mention two references. One of Carmona Master Simon, which show estimate that by different method, and some analysis of me and Bernard Paris in 1994. Okay. We have also used Agmon estimates for the so-called Harper model, which is related to almost Mathieu. Here the differentiation is replaced by discrete case. But you can work also in this context and try to prove Agmon estimate. So actually, for this model, you need to do Agmon estimate in the x variable, but then due to the invariance by Fourier transform, you have also to do Agmon estimate in the psi variable, the momentum pi. Okay. So, magnetic bottles in the semi-classical analysis. So now you don't have any V of X, and you want to measure some effect. So there are two questions. One is the behavior at infinity, and one is the semi-classical question. Maybe, so I have put a lot of references. But maybe the most interesting thing to mention is something which is in the spirit of the landscape function. So you are looking, in the magnetic case, you are looking for some quantum effect that you want to transfer to a new effective potential and to do the semi-classical Agmon estimate on the new model. So this is, in some sense, the same strategy that was used for the landscape function. You have a problem where V is not satisfactory. Here we have no V, but we have some magnetic potential. Then we first try to transfer the quantum effect to an effective potential. And so at least in 2D, because in higher dimensions, it's a little more difficult, but essentially this works in the same way, but we have not this inequality. Say, assuming B of x has constant sign, then you observe this trivial estimate. And so then the natural thing is to assume, to play with h B of x as a new effective electric potential. And so what would be the size of the effect? So you have again an Agmon distance related to B of x this time, or B of x minus infimum of B more precisely, and but you have h before, and so the size of the effect is in terms of the Agmon distance relative to B divided by square root of h. Recall that you have, before you have nabla phi square less than V, but V now is B, so you have h here, and you have phi over h. So this gives you the right scale is in square root of h. Okay, so this is just to mention a case, another case where you have to go through an effective potential to avoid this difficulty that classically, just looking at the classical symbol, you don't see how to get localization. Okay. So here is another example where you meet the same kind of problem. You have a potential V, which is the product x squared y squared. So it does not tend to infinity. If you want to measure, so here, the decay at infinity, it's better to start to find an effective potential, which is this one, for which tends to infinity, and to look at the decay for this. So I see that this chapter will be eliminated, this one also. Okay. And then just to finish, so you have heard about this. And so at the end, what we get in your approach, we get the question of decay estimate. So this model. So at the beginning, as far as I understand, you arrive to this, and then you choose the landscape function. But essentially, what is important is to play with this. So when u equal 1, this is v. When u is the landscape function, this is 1 over u. In the literature, we also meet for other question of splitting u equal the ground state. And then we get lambda, the ground state energy. As I have tried to mention, so as far as I understand, you don't have any semi-classical parameter at the end, and you want to do semi-classical analysis. And so, in some sense, you have to measure to follow the strategy, but being very careful with all the constants to obtain at the end that under certain conditions they are small. And this is your definition in some sense of the semi-classical regime, is that multiplying the tunneling effect by some other terms, this becomes small, and then you can compare the one-well problem to the global problem. Okay, so sorry to
thank you for this. Open for questions.
Yes.
Yes. I'm curious about the epsilon term in the exponential 1 minus epsilon.
Yes.
Why do you need it? Why cannot it be?
We need, so you come back to the, this was just at the beginning. Let's see. Sorry, I don't remember exactly where it was. No, it was before.
There were several
yes, yeah. Essentially, you want to divide in two parts. You want to control outside. So if I take exactly the Agmon distance, I will have 0 here. And I will have 0 here. I will have a problem. So I need to put some epsilon. Now, as I said, if I, for example, if I assume that V has a non-degenerate minimum, I take epsilon equal h ch log of h, and it's much more precise. That is, I will arrive, instead of 1 minus epsilon, I will arrive to h minus n exponential minus d of x over h, which is optimal in the sense that if you look to the so-called WKB solution, where it exists, this is what you have. So maybe I forget to mention one point here, the question of key. In the region where the Agmon distance is C infinity, then this is this phi of x. So the WKB solution, when it exists, the phase which appears here is the Agmon distance. But the Agmon distance to the wells is not C infinity everywhere. But the important fact is, so for the tunneling effect, you look at the minimal geodesics for the Agmon distance between the wells. And the important fact is that you can approximate in the neighborhood of this geodesics. You have the right, you can use the Agmon, the WKB approximation. It's not true everywhere, but it's true in the region where you have to compute the tunneling precisely. All the other contributions outside the neighborhood of the minimal geodesics are small due to Agmon estimate, but rough Agmon estimate.
Could you scroll through to landscape slides at the beginning?
Okay. We come back to the end.
Yes, sorry. But to the beginning of them, the punchline.
Oops, sorry.
Maybe further.
Later or further?
Muller-Payne reference. Where is it coming in?
Here?
No, before I said. Before.
Here?
Before.
Before.
The reference to Muller and Payne. What is it? Maybe before. That one, yes. The one you just have.
After that? Next. Okay. Yes, this I have not controlled, but this is Steinerberger, I would say that.
No, so he has corrected it. The Ceron reference was actually produced by Dimitri Benkov. And then Stefan
it's wrong. Sorry, I have not control. I reproduce.
Yeah, but that's there is the school which we are trying to stop from.
Okay.
So I mean, it's a very, very old paper, and nobody bothers to check, but it's wrong, and Denis...
So this is wrong. Okay.
Yeah, it's not in the paper, and Stefan has corrected it, and Denis has... but Denis has published it
as I said, I reproduced the Steinerberger introduction. Okay.
Sorry.
Okay, sorry.
Sorry, just...
Okay.
We're just trying to stop from rolling this crazy ball. Yeah, no,
Okay,
it's not.
so this
It's
is
not.
completely wrong. Okay. The expression of the fire will destroy this.
Sorry, yeah, just that you know there is this. It's a reference to reference. It's a paper from 20
I have no
something,
time
and
to
people are
control.
just.
Okay.
No. Yes, Doug?
Go a few more slides later, please.
Which direction?
Toward the end.
To the end. To the end.
That's one. So here, U is not the landscape necessarily, U can be any function.
When I arrive here, no, it's general.
And so if you choose, are there other useful choices of U other than the landscape function?
So what I see in this is that, for example, it's not necessary to impose, for example, a U equal 1. So the question is this choice optimal? But maybe in some cases it could be useful to look to an approximate solution where that you know better, and essentially after that, if you are doing Agmon estimate, I think this would be relatively stable. So you can have a choice that, so the question is, do we know, except numerically, do we know very well U? And so it could be, in some cases, I don't know, it could be better to have an explicit U with a less, the quotient LU divided by U is not so good, but you know it more explicitly, and then you can produce some result, which is not optimal. So there, I don't see in the approach, because you go through an effective potential, I don't see, except numerically, I don't see any proof that it's optimal. It gives some the best result that we know, but it's. And the other remark is maybe, as far as I understand, in the semi-classical context, if you have the semi-classical parameter at the beginning, to change U, to have U instead of V, it does not gain so much, because U is very close to, U is 1 over U is very close to V, at least formally. Yes?
I have one quick comment though, so at least in terms of the proof, and possibly in terms of the truth as well, there is a little bit of care that has to be taken there, because the fact that the reduced kinetic energy is actually reduced, the fact that we do not have a gradient term from, is very painful in the proofs. And we do use the exact nature of U.
I was sketchy, but in the magnetic case, the same, because you cannot simply.
Exactly.
It's a B.
So saying
you should still continue to keep some information of the kinetic term.
Exactly. So
I write very vaguely that you put 1 minus epsilon and epsilon. Is you play a little with that.
Right. So if we don't have 1 on the right hand side, I'm not saying that 1 is the best or optimal or whatever is his choice, but if it's an arbitrary function out of the scope, it's very possible that the lack of reduced kinetic energy will.
Okay, I think we have to thank the speaker again. Stop here the session.